Hello everyone. So I'm David, and I'm going to talk about this heterogeneous yielding on ductile fracture in aluminum alloys. So of course, my talk doesn't belong to fatigue per se, so I'm not going to talk about fatigue. It's just some good old monotonic loadings. As a context, so what we are doing nowadays, because we have of course bigger computers, we can run fine element analysis of material specimens or even small components with quite fine solid element meshes. And what we have observed is we do get pretty decent results when it comes to initiation of cracks and propagation of cracks in, let's say, ductile tearing. Or here, if we have more like a buckling problem, we have pretty good description of what happens. And in these simulations, we usually use some kind of a porous plasticity like the Gerson model, or we can also use metal plasticity and uncoupled damage models. And usually we get pretty decent predictions. So what we were thinking about in our group was that if we look at some material test specimens, like a single edge notch or tension test or shear test, and we think about the mesh size we are using, typically somewhere within 100 to 150 micrometers, maybe a bit smaller from time to time. And we compare these mesh sizes to the underlying microstructure that we are facing in aluminum alloys, in 6,000 alloys. What we find out is that actually your elements, they basically contain only very few grains per element. So when we move from one element to another, we are actually probing only a few grains every time. While these grains and their orientations, which we can think about as the texture of the alloy, is responsible for the isotopic plasticity in these aluminum alloys. So to get that isotopic plasticity, the common rule of thumb is to say that you need 1,000 grain orientations to have a representative texture and therefore a representative value for plastic anisotropy. But then, if I go back here, in one element, I only have a couple of grains, meaning that I'm very far away from this representative texture measurement. So that was the starting point for this study. So what we decided to do was to compare one element, one grain, let's say, type of approach, where every element will be representing a single grain to a polycrystal plasticity, which is a typical way of modeling anisotropic plasticity in aluminum alloys. And we want to find out what one gives compared to the other when it comes to prediction of failure and especially initiation in material test specimen. So ranging from uniaxial tension up to plane strain tension test. So typically in the medium to high stress flexibility range. For this, what we are going to do, we are going to use a virtual alloy. So it's a 1 millimeter thick sheet. It's a recrystallized texture, and all specimen will be meshed with an element size of around 70 micrometers. When it comes to modeling, of course, it's one element, one grain, so it means that we should use crystal plasticity on principle, but we decided to go for a single crystal yield surface proposed by Rona Kazaku and co-workers, and compare this single yield surface system to a Barla yield surface. The main motivation for this choice instead of crystal plasticity was computational power. It turns out to be an extremely efficient way of accounting for crystals without the cost of crystal plasticity. But of course, there are some caveats. There is nothing as a free lunch, so it's not always quantitative compared to crystal plasticity. To model failure, what we use is a modified Gerson model, in a sense that where you will find usually the von Mises equivalent stress, we insert either the Barla equivalent stress or the single crystal equivalent stress proposed by Rona Kazaku. We have work hardening, isotopic work hardening. In this work, we have considered only void growth, so we have neglected all that has to do with nucleation and shearing of voids. And when it comes to the final failure, I would say the last part of our model, we use this so-called softening condition to determine when FC, or call it coalescence, should take place. So the idea here is that once the elastic domains start to shrink, we consider that this is the point of localization, and we start to accelerate void growth or void evolution after that rate point, meaning that we get rid of one parameter basically. When it comes to fitting, what do we do? For the yield surface, we take 1000 grain orientation. We use a SACS approach, and we can generate a lot of data to calibrate the Barla yield surface. And we get, at the end of the day, a pretty decent fit. So the solid lines are the Barla yield surface, or this so-called homogenized modeling, while the dashed lines are coming from the aggregate of grains. For initial yield strength and work hardening, we did more like an RVE simulation where every single element represents one grain, and we apply periodic boundary conditions, etc. We can load it in Excel tension and recalibrate what should be the initial yield strength and work hardening of the Barla or homogenized model. And what we can see is that there is some differences between the blue curve, which is used in the Barla yield surface, or the resulting implicit stress strain curve, compared to what we use in the single crystal model, which is basically some kind of a Taylor factor due to the presence of the grains in the texture. For the porous plasticity parameters, we use standard values for the Vergaert constant. When it comes to the final damage part, we use an initial porosity of 0.5% and a critical porosity of 0.14. So that's where just some selected parameters which are in range with what we found on similar alloys. So what does the results give? So on the left-hand side, you have the stress strain curve or engineering stress strain curve from some tension tests taken at different orientation from the rolling or extrusion direction. On the top, we have the heterogeneous yielding model. On the bottom is the homogeneous yielding model. And overall, we get the exact same type of results. We get the same strength for the anisotropy in terms of stress level. And when it comes to failure, we also get the same ordering of the curves. But you can already see that there is a reduction of ductility when we go from the homogeneous to the heterogeneous model. If we look at the fields, like equivalent plastic strain field, at the end of the simulations, and put it back on the undeformed configuration, the very big difference is what the field look like. You can see that in the homogeneous yielding model, we get very smooth responsive, smooth distribution of plastic strain. But on the heterogeneous one, we get a lot of heterogeneity and gradients of plastic strain basically on the surface of the specimen. We also see that local failure strain, when the first element is deleted from the simulation, is varying with material orientation, and it's also quite different from the homogeneous one. So there are some inherent differences between this heterogeneous and the homogeneous modeling. If I compare to the other type of specimen we used, you can see again a small tension test here and some notches and plane strain tension. The orange curves are the homogeneous model. The blue curves are from this heterogeneous model there, where one grain is one element is one grain. And the different curves that you see are just different realization of the same texture. So it's just a different random draw from the texture. So what we see again, overall, the curves are pretty similar, especially up to maximum force. And then when we start to neck, we start to get much more differences between the homogeneous and the heterogeneous models. We also see that we start to get some scatter from the one grain, one element approaches, which obviously we don't get in the homogeneous one. So there are some kind of inherent scatter coming from the grains themselves. So if I, on the same type of specimen, plot the strain fields again, then we see the pretty similar outcome as before. The homogeneous yielding gives a very smooth distribution of the strain field. The heterogeneous one is a lot more gradients, kind of say off on the surfaces. And what we also see is that maybe a bit tough to see from here, but in the homogeneous yielding model, we get a more pronounced strain localization. So even though it's a very smooth or homogeneous model, the strains tend to localize more strongly than when we have this heterogeneous distributions of weights. If I try to look at some more local considerations, so what I did in this slide is to take the small NT3 sample and plotted out different quantities like the von Mises stress, equivalent plastic strain, porosity, and the stress state in the first element that experienced failure in the different simulations. And what we see, if I take the homogeneous curve, which is the model, which is a blue curve, failure initiated in the center of the specimen, which makes kind of sense. But the heterogeneous yielding models, the 5 realization of the same texture, the failure doesn't start in the same place. So it's basically moving across the cross-section from one simulation to another. And this, let's say, dispersion or scatter or whatever, however we call it, we can see that it has, could be of course quite related to the stress level. If you go from one grain to another, the stress level can go higher and lower depending upon the orientation of the grain. But the equivalent plastic strain field is also quite scattered. So depending upon the simulation and where failure occurs, we get that plastic strain develop faster or slower, which of course contributes again to the fracture part. In addition to the, let's say, the equivalent stresses and equivalent plastic strain, should also keep in mind that the from element to element. So to conclude this slide, if I come back to my original equation, what happens when we have these very fine solid element meshes, which capture only few grains? What we have observed is that from a global point of view, in yielding and strength, that doesn't matter, which is good news. On the other hand, when it comes to fracture, this heterogeneity that we lose by having a polycrystal plasticity could limit a lot ductility, basically. And that's what we have seen in this slide. And variation of texture, so basically one sample to another leads to a scatter, which is about the size of what we see in real experiments. And of course, where failure initiates is changing apparently from simulations to simulations. Thank you for your attention.